Hello, I'm Jacob, and allow me to share with you our research on using signed distance fields to achieve temporal compression of mesh-based volumetric video. First of all, what is volumetric video? Well, it can also be known as 3D video or a computer-generated hologram. It is directly captured from the real world and can be viewed from almost any angle. And there have been many prior works experimenting with it, such as creating a cultural heritage museum, tactical combat casualty care, volumetric combat, a parody of Mortal Kombat, and holoportation, which aims to replace in-person conference calls. Now, volumetric video has many competing formats, the most popular of which are colored point clouds and textured meshes. There are other formats such as NeRFs and Gaussian splats, however, these are less popular than the previous two. Most formats consist of just one 3D medium per frame, and this makes the video very large. For instance, the Sir Frederick dataset, seen on the right, is a 60-second video that comes to 15.5 gigabytes when uncompressed. And because of the size of these videos, the compression of volumetric video is a widely researched area. To talk about the formats, point clouds are relatively easy to understand. You have many points in 3D space that can possess a position, a color, a normal, or more per point. Their order is irrelevant, and you can add, remove, or alter the points without greatly affecting the overall representation. A mesh, on the other hand, is more visually pleasing to look at, but in general harder to compress. There are now three data structures to contend with: the attributes, the indices, and the textures. The indices in particular are very delicate, as an off by one error can be fatal to the representation. Now, signed distance fields are not commonly used to store volumetric video. They are a grid at distances to a surface with a negative interior, a positive exterior, and at zero, the surface is assumed to exist. More redundancy could mean more efficient compression, and so this work seeks to inject signed distance fields into existing mesh pipelines. Now, this was briefly explored by Tang et al., but only with respect to singular frames, and there is a notable research gap with temporal compression of signed distance fields. Our pipeline looks as follows. We first create a signed distance field from a mesh. We then compress the signed distance field, and then we regenerate the textures. Now, to create a signed distance field from a mesh, we first acknowledge that meshes are a paper-thin representation, and holes and other artifacts can make it difficult to determine the interior from the exterior. This is solved by Zhu and Barvik's method, which chooses to create an unsigned distance field around the whole representation. By choosing some value other than 0 to create the surface, you create an interior and an exterior shell. By removing the interior shell, you may then shrink the exterior and receive a rough approximation of the original mesh as a signed distance field. Now, to compress the signed distance field, we rely on singular value decomposition. In general, we split the signed distance field up into equally sized blocks and then decompose those further into U, D, and VT matrices. By retaining a percentage sum of the diagonal values of the D matrix, which we refer to as the energy, we can drastically reduce the data needed to represent the volumetric video while retaining most of the visual quality. We can then linearly map the U and V matrices onto 1 byte of data per value for even greater compression. If we want to do this across multiple frames, we need to first save an intermediary file of the signed distance fields to prevent accessing multiple signed distance fields in active memory at once. Now, this intermediary file is temporary and is promptly discarded once the volumetric video is fully compressed. As shown in the diagram to the right, one singular value is not enough for a single frame SVD, but appears to significantly represent a multi-frame SVD. For an action pose of multi-frame SVD, it becomes significantly choppier, although there are definite smooth areas such as the head and the leg. Now, to regenerate the textures, we need to recreate the UV coordinates and texture maps. This can be done with closest point interpolation between the original and recreated surfaces to copy the UV coordinates and the colors between. But if we wish to store the UV coordinates, we cannot do it with a signed distance field, as it only provides position data. As such, we use Tang et al.'s method to procedurally generate the UV coordinates at runtime. We allocate a spot on the texture per occupied block of the signed distance field. However, due to the intermediary file, we may take this a step further and allocate spots for blocks that will be occupied in preceding frames, even if they are not occupied in the current frame. This helps make the video more stable and benefits video compression, as you can see on the GIF to the right. Now, for testing, we choose the state-of-the-art to be Google Draco, largely because it's chosen as a state-of-the-art in many other volumetric video works. We also choose VSMC because it was chosen to be a base for a VDMC creation by MPEG, which aims to become a new standard for volumetric video compression of meshes. Now, this is not a perfect recreation. Due to time constraints, there is no keyframing of meshes. However, most of the pipeline remains intact. As for how we are testing our method, we are altering things like the SDF grid size, the amount of energy retained in the singular value decomposition, the amount of frames per batch of the temporal compression, as well as the effect of storing and reapplying signs from a signed distance field. The datasets we choose are the Surfrederick, Rafa, and Levy datasets from the Vologram set, the basketball dataset from the Tencent Dynamic Mesh database, as well as the punch, dodge, and death animations of volumetric combat. For our metrics, we are measuring the compression and decompression time, the file size ratio of the compressed versus original, the surface error measured through the chamfer distance, and the visual error measured through VMAF, which is a 2D metric, and in doing so, we record video from 8 different angles in Unity of each sequence for every test setting. Looking at the time data, it can be seen that Draco far outperforms the other methods in terms of compression speed. This is largely due to VSMC and Temporal SVD needing to regenerate their textures, whereas Draco may reuse the same textures as it reuses the same UV coordinates. Temporal SVD ranges between 4 to 9 hours to fully compress all 1.5 minutes of dataset video, so unfortunately it is not friendly for real-time compression. Looking at the decompression time, it can be seen to take between 2.5 and 45 minutes to fully decompress all 1.5 minutes of compressed video. So, unfortunately, it falls just short of real-time decompression. However, both of these times may be improved as the algorithm is iterated upon. Examining the chamfer error, we can see that VSMC experiences a very steep rise in error as the file size decreases. Draco seems to experience a relatively stable error. However, its entire effective file size is bound between those two data points. In order to decrease its file size further, it would need to edit its quantization level. Looking at the proposed method, we can see that altering either the grid size or the energy level experiences a very smooth trade-off between the file size and the chamfer error. We can see this is present across all other datasets as well, basketball being an exception, which will be talked about later. Looking instead at the VMAF 2D render score, it is given a value between 100 and 0 depending on how close to the original video it is. There are 3 lines for the minimum, maximum, and average score achieved across all 8 renders. We can see that the proposed method once again experiences a very smooth trade-off, assuming the grid size and the energy levels are edited. We can see that VSMC actually increases still a very steep degradation in terms of quality as the file size decreases even a small amount, and Draco is once again bound between the 2 data points shown. Once again, this is present across all other datasets. We can see that there is a little more variation, particularly with the Levy and Rafa dataset, where the proposed method dips to very low VMAF scores. However, it maintains a consistent value across all the other datasets. Instead, moving on to a visual comparison, we can see that Draco looks about the same as the original mesh. VSMC, on the other hand, while being much smaller than Draco on average, experiences quite a lot of flickering, both in terms of the geometry and the textures, which create a very unpleasant visual. Looking at the proposed method, we can see a much more stable texture in spite of some pinching, where the original looks mildly close to the Draco, while also drastically decreasing the file size as well. There are a handful of issues that are left as future work. For instance, when experiencing large holes in the mesh, the proposed method has to create an extremely large shell in order to fully enclose the mesh and create a assigned distance field. As can be seen, the basketball player has large holes in his feet, and because the shell size grew so big, his elbows are now part of his torso. So experimenting with different mesh to SDF methods is left as future work. In addition, one could experiment with adaptive distance fields such that less empty space is wasted on areas that effectively will never have geometry. And finally, VSMC recreation was missing a lot of features that VDMC likely will have, and so full comparison should be done when VDMC fully releases. Thank you for listening.